Okay, let's get into it. It's now 7:02, so we've had a little bit of time. I'm so glad to see so many faces here this evening. Names, we really weren't sure what to expect. It's hard to compete with playoff hockey, but we do appreciate seeing so many folks joining us. My name is Cassidy. I'm with the Edmonton Public Library. I am here to provide support as you need it in order to attend this event and just to offer any connection to the library that I can. We are, as always, so excited to be partnering with Future Energy Systems for this speaker series and for a number of other things that we've been working on, especially this past month. It's been a bit of a busy month. Lots going on for Science Odyssey, but really great partnership. It's always a joy for me to be able to jump on and learn something and provide a platform for everyone else to learn something too. Not much for me. I'm going to pass it over to Valerie in a moment here, but I did just want to let folks know, if you enjoy online and now in-person events like these, and you want to attend some others, you can always find everything that we have going on at epl.ca/events. We have a number of really great speakers coming up, including we're going to be talking to a couple people about David Garneau, specifically about the art on the new bridge crossing the river valley in Edmonton. So if you're interested in learning more about the Indigenous art that was put up underneath that bridge, you might want to check it out and join us. Okay, I'm going to pass it over to Valerie, but if you need help or support at any point, just let me know in the chat, or you also have my email from sending out the reminder yesterday. I am here for you.
Thank you so much, Cassidy. I feel like I need to check out the most recent events and find out what new things are coming. Welcome, everyone. We are thrilled to have you. My name is Valerie Miller. I'm the Outreach Coordinator for Future Energy Systems, and we really want to welcome you here today. Before getting started, I'd like to start with a land acknowledgement. We'd like to acknowledge that the University of Alberta, as well as the Strathcona branch of Edmonton Public Library, is located on Treaty 6 territory, a traditional gathering place for diverse Indigenous peoples, including the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Inuit, and many others whose histories, languages, and cultures continue to influence our vibrant community. As we explore energy systems, we want to acknowledge the territories, communities, and peoples that have been essential partners in that research. We are truly grateful to have the opportunity to work, study, and live on this land. And as Cassidy said, I'm from Future Energy Systems. So for anyone this is your first Future Energy Systems event, welcome. We welcome you. We have many events, and we hope to see you at them. But Future Energy Systems is a research program at the University of Alberta. It was launched in 2016 with $75 million from the Government of Canada's Canada First Research Excellence Fund to help Canada transition to a low net carbon energy economy. We focus on multidisciplinary research that develops the energy technologies of the near future, integrates them into today's infrastructure, and examines possible consequences for our society, economy, and environment. We also contribute to the development of solutions for challenges presented by our current energy system. There are over 100 research projects, over 150 researchers, over 900 grad students, postdocs, and other highly qualified personnel. And we are thrilled to invite one of those researchers here tonight for you to meet, to learn from, to ask all your burning questions. We would like to start by reminding current and future viewers that the opinions expressed by the speaker are not necessarily those of the Edmonton Public Library, Future Energy Systems, or the University of Alberta. So we are going to jump right in. We don't want to waste any more time with me talking. We want to get into this topic. So I am thrilled to introduce our speaker for tonight, Professor Mark Sequenel, who is a professor of engineering at the University of Alberta. His research interests are in the areas of analysis and computational design of energy systems, such as hydrogen polymer electrolyte fuel cells, polymer electrolyzers, flywheels, and cooling towers. That is a mouthful, as well as fabrication and characterization of these, finite element analysis, and multidisciplinary design optimization. And I am going to pass it over to you, Mark, to share your screen and introduce your topic for tonight. Thank you so much for joining us.
Valerie, and hi everyone. Thank you for joining me on a hockey night. I appreciate it. I didn't plan it this way. It just happened, which I'm glad that at least the Oilers qualified for the next round of the playoffs. Okay, so can everyone see my screen okay? Yeah. All right, so I'll get started. So again, thank you, Valerie, for the invitation, and everyone at FES. Thank you too for funding a lot of the work that we do in my lab. I really appreciate it, and thank you for to Cassidy and EPL for inviting me over to talk about fuel cells and about energy systems. So when they asked me to give this talk, I thought, what can I talk about that, or why do I do what I do? And I thought, well, I tend to work. Everything I do is towards transition to a zero-emission energy system. So what I want to show you a little bit is why I think this is important, some of the challenges that I think we will face from an engineering perspective, and also show you some numbers that hopefully highlight the challenges, and then also discuss the role that hydrogen can play within the transition towards a zero-emission energy system. So just to get started, why do I care so much about energy? I mean, that's what I do. That's what I teach at the U of A. That's what keeps me awake at night. I think it's because it is everything to us. If you carefully think about it, without energy, our quality of life would be that of the Middle Ages. We can eat bananas in Edmonton because we can transport them. We can feed 8 billion people because we can produce fertilizers. Because we can plow the land with machines. Like I have my own garden. I feed myself for about 3 weeks after I harvest all the potatoes and everything else. So I think it's very important to us. We take a shower, we take for granted that water has been treated already. So without plants like the one here in the picture by EPCOR that cleans the water for us, we probably would not have that. The water comes hot. Again, you need natural gas to heat that. You want to watch a movie, you put Netflix. Again, you need energy for that. So no energy means very little quality of life. I would say even more important than that, no one carries cash anymore. That means that basically we rely on the fact that there is a computer somewhere that is always on, that keeps track of every transaction that we do when we swipe those little cards. Imagine one day the computer doesn't turn on. I wouldn't even know how much money I have anymore. So everything that we do depends on having energy available. The same applies to mobility. Every time you take a plane, every time you take the car, every time you take the LRT, you depend on energy available for all this to happen. And I think that the ultimate energy is what allows us to have stable social institutions. Without free or without cheap energy, we would not be able to have the social structures that we have today. So that's why it keeps me awake at night, because we have to maintain it. And that's been a challenge of many generations, and now we have to transition it. So how did we manage to do it? This shows some of the evolution of energy consumption over the years. So if you can see my mouse there, this tracks from 95 to 2020, the amount of energy that we produce in the planet. And what you can see is two things. First of all, that oil, which is in green, red, that is natural gas, and the gray, that is coal. Fossil fuels basically are the biggest chunk of the energy that we produce and that we use in the world. It was like that in 95. It is the same in 2020. We also have nuclear in yellow. We also have hydro in blue. But basically, 85% of all of the energy that we consume today comes from fossil fuels. So as we look towards a zero emission, we are talking about completely redoing the way we supply currently energy to the world. The other thing that you can see is there is a slope here. So it's not only that we need to transition, but we're doing this game twice. We are trying to change things while we are adding more demand for energy on top of what we already have. The increase in demand is about 1.7% every year, in average, when you look at about 10 years. And this is all data from British Petroleum, but again, it's the same type of data that you could get from the International Energy Agency. So this is remarkable. Now, one nice thing, and one thing that hints that we are starting to transition, is that the orange box, the renewable part, the little fringe on the top, that's growing. And if you look at some of the statistics, right, they all coincide on sentences like this. So wind and solar capacity increased by a colossal 238 gigawatts in 2020, 50% larger than at any time in history. So everyone is pretty excited about the solar and wind that we have, right? Now, when they talk about watts, they talk about power, not energy. So I try to, in my excitement, I also try to look at how much energy that was. So I assume that, being optimistic, that these plants operate half the time, because only half the time the sun is shining, the other half is not. And then I transform this into energy. It turns out this is 0.65% of the total amount. So despite the colossal historic increase, basically renewables have not even been able to keep up with the increase in average energy demands in the system, right? So we need to transition, but the transition is of a scale that is significant. 238 gigawatts, by the way, is a lot of power plants. So it's not a small power plant. Nuclear power plant would be of the order of 1 gigawatt. So it's like building 238 nuclear plants. So what I would say is, over the past 25 years, I would summarize what we've been doing is burn, baby, burn. We burn everything we could find, and that's how we were able to maintain the quality of life that we've achieved today. Unfortunately, there are some problems with it. And I think the first one, I think the prime motivation is there is a lack of energy security, which is the most obvious, for example, today in Europe. Without energy, we all know, we talked about the stability of the institutions, so you wouldn't have that. That's also shown in this graph here on the top. This shows the price of oil in the y-axis versus years, and then the parts that are in gray are actually economic recessions. And so you can see every time there is a huge spike in the price of oil, it's followed by a recession. You can see it here, you can see it somewhere there, you can see it there again, you can see it there again, and now the price is high, so hopefully you don't see it in the next year or two, but basically it sort of tracks down quite well. This would explain too why the pioneers and the people that are more interested on a transition to a zero-emission economy or a renewable energy economy are the Europeans, because they also have the lowest reserves of fossil fuels, the lowest energy security. For us, it's a boom and bust economy, which is also not good. So that's the first problem. The second problem is air pollution. So if you drive all these cars, they generate particulates, they can generate NOx and SOx, so gases that can lead to acid rain. The result is about 4 million premature deaths a year, estimated in 2016. And of course, we all know about the greenhouse gases. So again, this graph here in the middle shows over the last million years, CO2 emissions in the atmosphere. And over the last millennia, we have never had CO2 emission, a concentration of CO2 in the atmosphere over around 300 until now, which we are at 420. The consequences of which we are discovering as we go along, but would include ocean acidification, mean increase in the mean average temperature, leading to extreme weather events, and the melting of the ice caps. Now, I wanted to, I find always when you're trying to tackle a problem, an equation helps. So I wanted to give you an idea of what the magnitude of the challenge is. And I like to do this with this equation here. I saw it at some point in the National Geographic. Basically tries to estimate the impact of anything that we do to the planet, but in this case would be our energy system by how many people use it. So P stands for population, how much people need that resource, which I call for affluence. So number of people, how much people need that technology, and then the T that stands for the effect that the technology would have, the ultimate effect impact on the planet. Right now, if we translate this into numbers, I could translate it into what you see on the equation in black that I try to point out with my mouse. In this case, I could say the population of the planet times GDP per person times energy per GDP times CO2 emissions produced per unit of energy that I have. And then I could try to look at every one of these numbers independently to basically estimate how I reduce the impact in terms of greenhouse gases emissions in this case. Right? So if I try to foresee the future, in the 50s, we were about 2 billion people. Now we are about 8 billion people, a little bit below. The projection is that we're going to be about 11 billion people by the end of the century. So basically, the first term in my equation is going up, not down. So the expectation is just because of population, the impact of our energy systems would go up. The second one talks about affluence. So how much energy we need to be happy, or how much energy we need basically to have a certain quality of life. And then this graph here in the middle shows GDP in the x-axis versus energy per capita consumption. Canada sits somewhere here in the middle of the graph. I'm sorry, this is so small. The trend is that the more affluent societies, as they move towards a higher GDP per capita, they also move towards a higher energy consumption. And most countries I concentrated are basically very low in the graph. That means that, again, if I try to foresee the future, and if I try to make a future where everyone achieves the standard of living that we are lucky to have in places like Canada, Europe, then you would then expect, again, a rise. And looking at that slope and looking at how much people consume and how much we consume, I would say it's a factor of 5. So that means I have two stressors that end up adding to about 7 times more impact than what we had before, right? So now what we need to do as engineers is this transition box. I need to put some factor here such that I reverse that increase of 7 times. And not only reverse it, but worse than that, because if you think of our current energy systems, this is a CO2 emissions per year. Again, I'm producing a lot of CO2 as it is. And the problem that we have now, I equate it to a bathtub, right? We have already put the CO2 in the atmosphere to the level that is close to overflowing the bathtub. The only thing I'm doing with the impact now of CO2 is I'm changing the flow in the tap. So the only way this is not going to overflow is if I close the tap, not even if I keep it flowing. If I improve my system by a factor of 7, then with efficiency or whatever it is, I would only maintain the tap flowing at the same rate. That means that basically the only solution I have here is to put a 0. If I multiply anything by 0, if I completely reduce or eliminate emissions from my energy system, then I might have a chance. Otherwise, you always will have to be fighting the other factors in front of it that all tend to make your energy systems more impactful. Okay, so that's what we appear to have to do. And then I see basically 3 big problems as we try to transition. One is a problem of magnitude. So again, if you look at the amount of energy that we consume, you divide it by the number of people, it turns out that every single person in the planet on average consumes about 2,000 kilograms of oil a year. So again, that's reflect on that. Imagine if you had to go and take buckets of oil from a well and store them yourself for a year. You have to do 2,000 of this. Right? So a bucket is 5 kilos. Look at the amount of trips. An average Canadian, 5,000 kilograms of oil a year. That's the amount of energy that we now have to replace into some other form, say solar or wind. The second problem I see is one of timescales. So when you talk about global warming, you're talking about something that will affect you in a 10, 20 years time. So again, if you look at the IPCC report, it says global warming is likely to reach 1.5 degrees between 2030 and 2050. And to us, that sounds close. But again, if you live in another country where they still have to walk to get water, they are more worried about 3 days without water equals death. That's basically how much a human can live without water. So how do you tell someone that does not have water security that he cannot use energy that is available because CO2 emissions will increase? That's a problem that I think we don't discuss enough. And then the third problem is that we always think about climate change from a Western perspective. And in the 70s, as you can see in this graph, this is energy consumption, depending on the region. It was a problem. Even in the 90s, I would say, yeah, the West was a problem. But as we move towards the 2020s and the new century, we are now not even half of the amount of energy that is consumed in the world. There are many others, which means that basically we have a problem that we have to agree on at a global scale. And at this point, every country has different priorities. It's not a common priority to say CO2 is the most important thing. For some is water, right? And so this leads us to a little bit of a Faustian dilemma where we know what is right, but we might want to look at we might think that we have other priorities in the shorter term, right? So again, I like this quote here from Faust book that says the rascals meaning fossil fuels, offers wealth untold, but gives the glitter, not the gold. That's, I think, where we are, right? You need the shininess because that's what sells. Yeah. So I would say we have to transition. It's clear that we have to, but I think it's not an opportunity, it's a challenge. I'm a little bit concerned when you try to look at what with the transition is simply an opportunity to make money. I think it's a necessity. And it's actually a very big problem that we're facing, one of the biggest I can see in terms of size and scale of transition. So with that in mind, I would like to show some of the new data that maybe shows a way into the future and some of the challenges that we might face. So the first thing that is actually exciting, I think, and matches with some of the increase in renewables that you've seen in the previous years, is that for the first time, solar and wind actually cost less per megawatt hour or per unit energy than any other resource that can be harvested. That means that basically this is great because they are the ones that do not produce any CO2, right? So these should become our main staple for transition. Now, again, it's great that they are the main staple, but we need to understand the magnitude of the problem. So when you put 2 panels on your roof, you need to understand how much you're affecting the global scale of the problem, right? So what I did here is I tried to calculate how many panels we would need in order to meet just the increase in demand that I was showing before, that 1.7%, that is the year-to-year increase in energy demands. So I made some assumptions here. I assumed that the solar plants runs at a capacity factor of 25%, which is the average worldwide, meaning that you're going to get sun only half the time. And then the other half is cloudy, so you get 25. That you have an efficiency of 25%, which is the average silicon cell. And then to make myself slightly happy, I took the solar irradiation per meter square that you get at the surface of the atmosphere. So this is the maximum amount of watts that you're going to get from the sun reaching the planet. And then if you look at all these numbers and you make the division to get to this 1.7% increase, the number of panels that you need to install, not even including land, which will be more because you need to space them a little bit, is 3,500 kilometers square, which turns out to be bigger than the size of Luxembourg and about 1/10 the size of Switzerland. Yeah. Now, it is possible because I just showed you before last year, we met 0.6%, not 1.7, but 0.6%. So we are working at scales that are similar. But this is the magnitude of solar panel deployment that you have to do. Either that or wind, right? You would also have numbers for wind that are large. So if you want to do this, that's great, right? So that's the good news. We have now the resources to do it, but it will require a lot of commitment. Now, what are the biggest challenges to the transition? One of the biggest challenges that I see, so I go into this movie, The Good, the Bad, and the Ugly. I covered the good. The first bad is something that I read in an article recently called the locked-in effect. So all these renewable resources are the cheapest one to build right now. But what happens if you don't have to build anything? So I tried to look at some of the power plants that we have in Alberta, the largest ones. So these are the largest plants that I could find in Wikipedia. And if you look at their startup date, Sundance 1970, Genesee 1989. Now they are changing from coal to natural gas, but again, all the plant was built in the 89. The burners are being modified. Keephills 83. So these ones, the first three, are all in the gigawatt scale, and then we get into the megawatt scale. And then again, these are all only two. The last three are newer. These plants were built before Alberta was deregulated. So they were built with taxpayers' money, not with companies' money. Now you're asking companies to make very large investment in generation that they never had to make. And again, some are doing it. For example, there is this plant, 300 megawatts. There is this other plant, the Shepherd, 800 megawatts. But it's a lot of cash that only will pay off much later. And on top of that, why would they do that investment when they already have a plant in place? So there is nothing cheaper than what already exists. So that's the first challenge. The second challenge as you transition is solar and wind give you electrons, but not everything runs on electrons. So for example, this is a chart that is called the demand and supply chart from the US Department of Energy or US Energy Information Administration. It shows for every sector that uses energy, where does the energy come from? If you look at transportation, 90% of the energy used for transportation comes from petroleum. So if you produce electrons, you cannot use them yet. There are no electric planes. There are no electric long-haul trucks. And so producing electrons is great, but I also require something that will displace fossil fuels from sectors that are not available to natural gas, to electrons. Same for residential and commercial. 42% of the energy from residential comes from natural gas because of heating. Commercial, 38% comes from natural gas. So I need something else other than electrons. And maybe the last one, again, we put wind, we put solar, these resources are intermittent. So on a day scale, how does it manifest itself? It manifests itself in that, for example, in California, this is the demand versus time. During the hours of sunlight, you have a reduction in demand because the solar panels provide energy for the houses. But then at about 6 p.m., between 3 and 6 p.m., where the sun starts to come down, you lose that solar energy. And then you have to ramp up, the demand ramps up very, very quickly. That's what they call a duct curve because it looks like a duct. It didn't happen in 2019, but it's happened in the past 3-4 years as solar got deployed. You need to meet that demand and you don't have the sun. So that means that you still need something, right? And I think you now know what that is. Yeah, so that's a natural gas power plant again. So we continue to rely on fossil fuels. For northern places like Edmonton, if you look at the sun trajectory again, what you see is that the sun and you've all experienced this, the sun trajectory in the winter months is actually much lower. So the sun doesn't rise very high and it actually sets sooner as well. So this is a graph that I collected from data from this website here. It shows the hours of sunlight in Edmonton in blue. So in December and January, you're looking at only 8 hours of sunlight versus 16 in the summer. And then the red line shows the altitude of the sun, the maximum altitude in the middle of the day, which again, in Edmonton in December and January is 11 degrees. That means that your panels have to be almost completely vertical and one panel will block the other panel. So you, again, lose a lot of the solar. And so that means that we need to store energy seasonally if we want to rely only in the sun. Wind is a little bit better than that, but even wind doesn't blow as much during cold spells, for example. So basically, I went from the good, the bad, and the ugly to another story. If we want to deploy everything, there is the good thing that we have solar and wind, but we also need to store some of the energy in the summer for the winter, right? So we cannot be like a grasshopper and just live day to day, like we've been doing now with fossil fuels, where we basically use the energy when we need it. We now need to use solar and wind to make our own reserves that have to last us through the winter or part of the winter. Okay, so to summarize, I would say the future means a lot more wind and solar. But if we depend only on electrical energy, then we need to be concerned that 60% of the energy that we use is actually not in the form of electrons. So we need a way to enter those systems. Ideally, we can find some storage solution that allows us to allow the electrons to access those sectors. The other thing you need to worry about is this intermittency between supply and demand. So again, you need more storage. And so the summary of all this is I need to be, again, the ant and worry about not only solar and wind deployment, but together with it, also look at deployment of energy storage at the short-term scale to stabilize the grid, but also the long-term scales to be able to store energy in the summer for the winter. So if you think of that, then you need to also pick some solutions, right? So this graph here I borrowed from Fraunhofer ISI, national lab in Germany. In the y-axis, they show the power that different technologies can provide, and the x-axis shows the amount of energy they contain. So again, we have all sorts of technologies: flywheels, battery electric vehicles, lithium-ion batteries, lead-acid batteries, some other types of batteries. But if you look at a lot of energy, right? When you try to be, again, that ant, the only thing that can store energy of the order of days and months are synthetic fuels. So chemical storage, like hydrogen and synthetic natural gas, or mechanical ways of storing energy, like compressed air and pump hydro. But even these two are of the order of a day. The electric vehicles sit here. I did some calculations this morning to try to highlight that a little bit. So I look at the number of cars registered in Alberta, which is about 3 million. I look at the battery of a Tesla Model 3, and then I try to understand how much energy is stored in all of those cars. And so if you connect all of those cars together and you try to pull energy from them, it would basically allow you to power the grid according to the amount of power capacity that we have for about a day. So total amount of energy, I would say 6 hours. If you do it for, if you only look at electricity, about a day or so, right? So we need a lot bigger storage. We're talking about reservoir size storage. So that's where hydrogen comes into the picture. It does have that flexibility that I can take solar electrons, I can transform them into a fuel. This fuel can be stored underground into very, very large scale reservoirs. And then once I have the fuel, I have also the flexibility to use it in many ways. I can blend it into the natural gas grid to use it as a fuel for heating. I can use it to refuel cars and then make the electrons in the car directly in a fuel cell. I can use it to produce electricity, which again, I can use back for the grid. And I can also produce it from fossil fuels, right? I can even make fossil fuels if I wanted. So it allows me to go back and forth and store large quantities. It also allows me to use it as a feedstock for many industrial processes, which I will talk in a second. So that's what I want to focus on. The second part of the talk is talk about hydrogen, how to make it, how to consume it. But before that, again, everyone seems to be talking about hydrogen, and I wanted to explain maybe why now is a better time, because we have known of hydrogen for a long, long time. So long time means 1972, there was a paper by Bockris and Science where he already wrote this. The electricity they make, they meaning offshore wind turbines, would be converted on site to hydrogen and oxygen by electrolysis. The hydrogen would be piped to distribution stations and thereafter sent to factories and homes. So that was 72. So now we are 50 years later. What has changed? And I think what has changed is that wind and solar have become reasonable in price, and that we have lost the other alternative that was the winning proposition. I mean, nothing beats making a hole and getting natural gas out of the ground until you need to worry about CO2. So I think now we're at the stage where we can again look at hydrogen to fulfill the circular economy, where you would have electricity. You would use electricity if you can, as is, but any excess electricity that you have, you would then use to split water, make hydrogen, store it in large quantities. And when I talk about large quantities, I'm talking about seasonable storage, and then use it afterwards in fuel cells, or again, as a fuel, whatever is most efficient, and then close the cycle with the water being produced as the only byproduct. The other reason I think why now is a better time is because it allows us to still use some of the resources that we have now, like natural gas, to produce the hydrogen and store the CO2. And I'll show you some technologies that can be used for that, even nuclear. So it allows us to create our own fuels and then transition slowly. And it allows us to displace a lot more things, not just electricity. Like, for example, ammonia production, the CO2 emissions from ammonia production can be reduced by 45%, from refining by 47%. Methanol production, again, I can reduce CO2 emissions, right? This is a graph by Brian Pipobar at NREL in the US, where they estimated that they could reach a 45% reduction in carbon emissions by 2050. And with this, I'm gonna stop for a second to let you guys ask questions before I move to the actual hydrogen energy.
Wonderful. Thank you so much. It's been a great start so far. I feel like I've learned so much new stuff. For everyone in the audience, feel free to pop your questions in the chat and I will moderate those. And you can do that throughout the entire talk. So that way, if you've got a question that's burning, you can just type it out and I will ask it during one of our Q&A sections. The first question that we have from the audience is related to something you said, I think on your first slide, but kind of about that just transition. So we talked about a lot of new technologies, but many of these new technologies are more accessible or affordable in developed countries. So how can we address issues of developing countries needing to produce energy while also limiting emissions? So that just transition, that is a very deep question. It's definitely not got an easy answer, but if you have any perspectives. Oh, you are muted.
Still muted.
Sorry, can you hear me now?
We can hear you now.
Yeah, sorry. So I think that's where I go to the Faustian dilemma, right? I think a lot of the hydrogen hype these days, it's all about how we're going to live better and how we're going to produce jobs and make money. You cannot help a lot of people if what you want to do is to live better than the others. And again, that's the Faustian dilemma of, do you want to do the right thing or do you want to do what's good for you? If you want to deploy solar technologies, I mean, I will give you an example, yeah? We all worry about the IP on solar panels, yeah? Like the Germans or the Europeans, they say, well, you know, we should all deploy solar energy. Well, make the IP freely available to African countries. Stop trying to sell them solar panels. Maybe give them the solar panels. But otherwise, you're just trying to bleed blood out of a stone. So if you just try to charge them for putting solar panels when they don't have anything, that leads to a little bit of a problem. So what do we want? What do we want? Do we want to all live well in this planet with 10 billion people, or do we, the West, want to live well at the expense of the other ones not producing? Maybe that's one of the questions that we need to eventually answer. And maybe that's more a socio-political question than it is an engineering question. But I think the technologies are there. We need to deploy them everywhere. That's not an engineering question anymore, how you deploy them, right?
Yeah, and I think it leads really nicely to the next question that we had was, can we use any of the lessons of COVID and how many countries came together with technology and knowledge to guide how we can go together in climate change and addressing that challenge?
Did we come together?
I'm gonna stay out of that.
I would leave this a little bit as a question. Did we come together? I would say when COVID started, I thought this would be a great example. It would either show that because if you think about it, it's a problem that requires 3 milliliters per person of something, not 180 kilograms per person of something, right? So to some degree, all we needed to do is philosophically agree. We didn't need to actually go and put 3,000 kilometers square of solar panels anywhere. All we needed to do is to think about it, agree, and then what did we do? We closed borders. Everyone had different policy up to this day. And the vaccine is still not freely available. So non-industrialized countries still not have a vaccine. And as far as I can tell, Pfizer hasn't said, here's the formula, go and make it. I think they still charge everyone. So what have we learned? We've learned exactly what I said in the previous question, that we didn't treat it as a challenge for everyone to live better. We treated it as an opportunity to make money. Maybe we have to learn from it, but it's not the good things. I think we have to learn to do it even better. Because at the end of the day, what did we do with COVID? We did the same thing at the Middle Ages. Eventually, we just said, we'll take our masks off and save your own soul. Other than the vaccine. So the science works. And if we can agree to do things properly, we can, right? But the agreeing is complicated. Yeah.
Absolutely. I think that answers another one of the questions we got was, technologically, scientifically, we have what we need to address many of these challenges, but it's societally that we need to figure out how we address those challenges.
Yeah, I would agree with that. I would also say from experience, only recently I started to play with the garden. I hope everyone has a chance to understand only how difficult it is to live out of your own food, because that gives you a degree of, I think, understanding of how lucky we are. Like it's amazing. Like it's amazing that you can go to a store and buy a bag of potatoes that basically would require, at least in my garden, maybe my soil is very bad, but it basically requires, I would say, about 3 feet by 7 feet of land. And you have to like plot it, water it, and then go and pick this whole thing up. And it costs you $3. Yeah, it's amazing the disconnect we have now between effort and pricing of things. And until we, and this disconnect is because someone is working at a much lower price somehow, right? I mean, you have machines and technologies which help a whole lot, but something is disconnected that it takes you so much work, and yet 1 hour of your work, like me teaching for 1 hour, looking at my salary, right, is the same as me going to the garden and spending a week. Yeah, and the same would apply to a t-shirt. I can buy a t-shirt for $10. But if I had to do it myself, I would have to spend, I don't know, 50 hours, maybe more, of my own time. So I think some of this comes from labor that is maybe unreasonable, and some of it comes from how good our engineering has become, that we have taken a task that a normal person would take 50 hours, and it can be turned into, with a little bit of energy, a machine doing it by itself, right? So we are very resourceful people. I mean, we can transition into anything. When we know what we want, I think humans are amazing at being smart.
Just need the right motivation. So the next question we have is, what is the efficiency of creating hydrogen with electricity and then converting it back to electricity to use?
Yeah, so that's the second part of the talk, but I would say it will depend how you do it. If you go electric, about 40%, 50%. Again, depends how you do it, depends how you store it. So 50 being very optimistic, 30 being pessimistic.
Okay, and we'll jump into more to that in the second half. The next question we have is related to those different sources of energy. So why are we focusing on wind and solar, which have an energy return on investment of 5 to 15 times, when nuclear has an energy return on investment of 100 times and does not require the ecological destruction from mining that mass production of solar, wind, and batteries would require?
That's a good question. I think, well, from my point of view, I think nuclear is great, but I don't think that we will. Again, it's a worldwide problem. Last time I recall, last country that have a nuclear program got into many problems, right? So because between a nuclear program and then doing enrichment that would lead to nuclear weapons is not a big deal. And then you're having to pick one country versus another, and that can lead to a lot of socio-political impacts. The other one would be how people assess risk. So if you don't trust a country a whole lot, will you trust it to run a power plant? I mean, we have the example of Chernobyl. So I think it's all down to human interactions, but nuclear has challenges that the other ones do not have. I cannot create an enrichment program, or I don't need to create an enrichment program to run a solar plant, but I do need it for nuclear. Having said that, it would be great. Yeah. In Canada, we tried to put a nuclear waste storage facility, and they did all the plans and everything. The people that live around never agreed to have it in there. In the US, they also have been trying to put a nuclear waste facility. They never agreed. So until these problems are solved, it's going to be an uphill battle, even more than for the other ones. But I agree with you. I think we should look at everything. I focus on nuclear, on solar and wind, because they are the cheapest one right now in terms of cost. Nuclear is another option. I think the idea of storing energy for transportation, for example, still would apply. So you would still need some carrier as a fuel. And I hope that answers the question. Long answer to your question, but and completely agree with the ROI, your energy return on investing values.
Wonderful. Thank you for that question. They've just followed it up with a comment that apparently Finland just commissioned a new nuclear plant last year. So just if anyone wants to know more about that, you can do some research on Finland. We have tons more questions, but I want to make sure we have time to get to the second half. So I'm going to pass it back to you and then keep sending me your questions and we will ask them at the end of the talk.
Right. Thank you, Valerie. So after the intermission, we'll do part 2, which is the hydrogen energy. So I wanted to talk about production, storage, usage, and I thought I would do a demo with you as well. So I have a little setup here, and we'll try to see if we can make a live demo to see how the technology works. Okay, so now that we have decided on hydrogen, how can I make it, right? So the nice thing with hydrogen is it can be produced from many different sources. So you can use fossil fuels to produce hydrogen, renewable energies, and again, nuclear energy, talking about nuclear energy in the last question. From fossil fuels, what you can do is if you have natural gas, you can use steam methane reforming, which I will talk in the next slide, to basically break the methane molecules into carbon dioxide and hydrogen. If you bend the hydrogen dioxide into the atmosphere, then you end up with what's called as brown hydrogen. If on the other hand, you do storage of the CO2, then you would have what's called blue hydrogen. So from natural gas, I can do blue hydrogen by doing, again, the same process of steam methane reforming, but then storing the CO2 underground. Or the other process that you can follow is you can actually heat the natural gas to very high temperatures of the order of 1,000 degrees, and then the molecule will break apart. The bond between the carbon and the hydrogen breaks, and then you can have solid carbon that forms in the reactor where you are doing this, and pure hydrogen that can be then used as a fuel. And then the third option that you have is green hydrogen, which is the one that we were discussing before, where you can use solar and wind and via electrolysis split water to then produce hydrogen, which I think is the ultimate path because it has no emissions throughout the whole pathway, and you don't need to worry about storing anything. From nuclear, you can also create hydrogen either by heating the water until you thermally crack the water through several thermal cycles, or again, you can use the electrons for electrolysis. So in the case of steam methane reforming, which is the way we produce a lot of the hydrogen in the province, for example, nowadays, what you do is you would take your natural gas from the natural gas reservoir, you take the sulfur away, just because otherwise you would form sulfur oxides, which are not good, so you can remove it at the source first. Then you mix it with steam, and both of these you heat up in what's called the steam reforming step in a reactor, such that you end up with a mixture of hydrogen and carbon monoxide. And then at this stage, what you do is you take this mixture, you cool it, you add water to it, and then the CO becomes CO2 and hydrogen. So you end up with a bunch of hydrogen and some CO2 that in the last stage you separate. So you take the hydrogen out and you separate it from any leftover methane that has not reacted and the CO2. And then you could take the CO2 and store it underground, which is the next stage. This has an efficiency about 75 to 80% from hydrogen, the energy in the hydrogen that comes out to the energy that came in. Now, this would be brown hydrogen, but if we want to create blue hydrogen, we have to store it. That comes, however, at a cost, and it also has some limited capacity. So in this picture here, I show some of the places where you can store CO2. So now we usually do it in depleted oil and gas fields, or in active oil wells when we want to do enhanced oil recovery. We could also put it in coal beds. All these are very high integrity ways of storing hydrogen, and they have low environmental risk. They also have limited capacity. So when I looked at the CO2 emissions in the atmosphere, what I did here is I tried to convert this into amount of carbon by simply get the mass of CO2 compared to the mass of carbon. And it turned out that that was about 9 gigatons of carbon produced a year. So that means that the storage capacity that I would have is a little bit low, right? It can be used for a while, but eventually you're going to be stuck to having to do it in deep aquifers and oceans, and this starts to have a much more costly. Well, costly. It's a much more environmental, dangerous game to play. You also have costs associated with it. So this is the price of storing a ton a number of dollars to store a ton of CO2. So again, if I have CO2 that is concentrated, then the cost is quite low, like you can see here. So then this is SMR for hydrogen. You need to pay between $50 and $100 to store a ton of CO2. That's an estimate from the International Energy Agency. If you do it for places that are less concentrated, then it costs more. So a power plant, for example, you would take the flue gas from the power plant, the exhaust, and that doesn't have so much CO2, so it costs you more. And if you do direct capture from the atmosphere, because we only have 4 parts per million, then it takes even more energy or costs more to collect that CO2, both energy and cost. Another pathway that I showed was pyrolysis. So that's one example of the things that we do at the U of A. This is one of the future energy projects, and this is in collaboration with a colleague here in the mechanical engineering department. Well, what we are trying to do is directly pyrolyze the methane molecule to produce hydrogen and carbon. So we build a little reactor, which you can see a picture of here in the middle, where we can take methane. The methane goes into this reactor that you see here that is in a furnace. And then we heat up the methane for a certain amount of time. And then we open the valve and look at the amount of gas that has come out. And what we find is that if you wait a few minutes, then about half of the gas that comes out is already hydrogen. And so we are studying the different models that can be used to predict how much carbon and how much hydrogen is generated, and then trying to build models to then be able to scale this into eventually a full reactor. The third pathway was the green hydrogen. So this is electrolysis. There are 4 main technologies that use electrolysis. Alkaline electrolyzer is the most mature. Proton exchange membrane is the one that is the state of the art, I would say. And then alkaline exchange and solid oxide electrolysis are 2 that are basically a more advanced version, I would say, to the current technology that we are trying to study. In all these, the principle of operation is basically similar. This can be shown here in the picture on the right, where I'm looking at polymer electrolyte, proton exchange membrane electrolyzer. The idea is you bring water on one side. The water will, when an electrical potential is applied to this electrode, will split into oxygen, protons, and electrons. Then this membrane in yellow here in the middle is gas tight, so it doesn't allow the oxygen to travel across, but it allows protons to travel across. So the protons would go to the other side where they combine to form hydrogen. Following this reaction, protons plus electrons from your power source are leading to hydrogen, and then this hydrogen is collected and stored in a bottle. This system basically is characterized by what's called a polarization curve, which I show here, and shows the voltage in the y-axis, the current in the x-axis. Ideally, you would want this flat line I put here in red. So ideally, what you would want is that you keep the same voltage all the time, and you can run this electrolyzer at any current. That would mean that a very small device would be able to produce all the hydrogen you want, right? The reality of it is that as you try to produce more hydrogen with the same device, the curve looks more like the one that you see there in red. And then the gap between these 2 is an efficiency loss. So ideally, they would run at 1.2 volts and then make hydrogen forever. The reality is there is an extra voltage that is used to drive the reactions. And this is a loss of energy that we need to understand. So back to that efficiency question that you guys were asking before. If you run a low current density your device, then your efficiency is quite high. But if you try to produce a lot of hydrogen quickly in a device, then you will pay efficiency or energy loss, penalty loss. In terms of efficiency, again, operating at the normal range of an electrolyzer, for the 3 technologies that we have today, the estimated efficiencies are of the order of 60 to 70% for alkaline, again, 60% to 56% for PEM, and 70 to 80 for this very high temperature electrolysis. This guy has a lower efficiency, but it compresses the hydrogen already. And then this is sort of the lifetime of the stack. In terms of how much it costs, what you can see here is the price of a kilogram of hydrogen. And then the blue, or the part in purple, is the cost of the electrolyzer unit, depending on the hours of operations, how much you would amortize it. And then the blue part is the addition of the price of electricity. So with an electrolyzer, if you don't use it at all, right, the price of a kilogram of hydrogen is infinity, because you just bought a bunch of equipment and you're not selling anything almost. So to amortize it, you would have to sell it at a very high cost. If you operate it in this window here, which would be the optimal load for the electrolyzer system, then the cost of a kilogram of hydrogen is about $8 per kilowatt with current electricity prices. That's the estimate, and current technology. Of course, as the electricity prices, as you have more excess renewable energy, this blue box should eventually drop, right? Because the cost of electricity would also eventually drop. All right, so in this area, mainly the things that you can work on to try to make the technology more feasible is reduce the cost so that this purple part is even lower, and also improve the durability. Because if I make one device and the device will last you 50 years, then instead of having to replace it every 5 years, that would also bring the cost of the electricity production or the hydrogen production. So that's one of the things that we do in our lab. Again, so this is another project sponsored by Future Energy Systems, where what we try to do is try to look at different electrode designs. So you have that yellow layer and the layers that are on the side that catalyze the reactions. Many materials can catalyze those reactions, and some do it very well. All this is happening at scales of 1 micron. So this is a picture of an electrode. This is about 3 microns in thickness. And this is done with an electron microscope. So these are some of the initial curves that we got. On the top here, you can see they're quite steep as you go to high currents, while the latest version of our electrolyzers are much lower. We achieve this again by doing things like adding pore formers. We do this by changing materials. So we work with proton exchange membranes, but also alkaline membranes. We do this via simulation. And our aim is, again, to improve these electrolyzers, also to improve the durability so that the performance stays more or less the same, even if we operate them for days. And this aligns with the goal in the Department of Energy in the US, which currently has a program called the Hydrogen Shot, where their goal is to produce 1 kilogram of hydrogen for $1 within the next decade by improving electrolysis and also by the deployment of renewable sources. Okay, everyone talks about hydrogen and they like to talk about the Heidelberg. There's a video documentary that was done of it, or talk about the fact that hydrogen is hard to store. So I wanted to cover that a little bit in the presentation. So first I'll talk about fire, and then we'll talk about space. Fire-wise, this is again a Department of Energy in the US test, where what they did is try to understand how fuel cell vehicle would react in the case of a sudden hole in the tank. And they did this for a hydrogen vehicle. They did this for a gasoline vehicle. So in both cases, what they did is they puncture the tank, the fuel tanks, and then they put an ignition source close by. So what happens with hydrogen, like any fuel, is flammable, yeah? But because hydrogen is so light and it's stored at high pressure, what happened is when it found the ignition source, the flame went upwards and it went out of the tank because the fuel is leaving the gas or leaving the storage tank at high velocity. So basically you end up with a flame or a lighter, right? So the flame burned upwards and outwards away from the vehicle, which means that after the whole flame extinguished, there was little damage to the car. In the case of a gasoline fire, what happens is that the fuel cannot dissipate. So it pulls at the bottom of the vehicle, it finds the ignition source, and then the fire happens where the car is, And so eventually you had an explosion. Yeah, so to some degree, in terms of accidents, hydrogen is actually not so bad as people might think because of the high pressure. This link here shows some experiments that people have done where they actually shot hydrogen tanks to see what the behavior was. They took a Toyota Mirai and they rear-ended it to see what would happen. And in most cases, or in the cases shown, it wasn't a big issue. Again, the advantage is the density is so low, right? So again, for gasoline, it doesn't pool. If I compare it to methane, which is another gas, again, the density is very low, the diffusion is very high, so the hydrogen is hard to concentrate because it wants to disperse and it wants to go upwards. The only problem that it has a very low ignition energy point. So it's very easy to ignite, right? The only times I've seen issues with hydrogen is someone has left a bottle open and then a spark from static has ignited that flame. And then you do have a problem, right? Because you have an open flame, and if you're in the way of that open flame, you're gonna burn down. But in general, as long as you understand the properties of the gas, it can be dealt with rather easily or safely. I've had a hydrogen lab with hydrogen for 12 years, and we had not had a single incident yet. Fingers crossed. In terms of storage, what can you do? Well, there are many things that you can do. These are 4 possible solutions for storage. The first one is, I think, the most conventional one and the one that requires least amount of energy, which is basically compress the hydrogen into your tank. That's what the current fuel cell vehicles do. This graph here shows the volume of your tank compared to the pressure that you need to apply. So if you apply if your pressure is only 10 times atmospheric pressure, you need 500 liters to store 4 kilograms of hydrogen. But when you go to 700 bars, so 700 atmospheres of pressure, then with about 75 liters, you can store 4 kilograms of hydrogen, which is similar to what the Toyota Mirai has. So what they have in their fuel cell car is 5.6 kilograms of hydrogen at about 700 bar, and that gives them a range of 650 kilometers as for the EPA registered range. And again, they do this by, in the fuel cell vehicle, putting 3 tanks that are sitting, one between the passenger seat and the driving seat, and then 2 at the back of the vehicle, which you can see also there in yellow. If you need to make the volume even smaller, so when would that apply? If you're trying to make a plane, right? Then your space is of the essence. Then you can also liquefy the hydrogen. That's expensive because hydrogen only liquefies at minus 260 degrees C. So this is a cryogenic fluid, which is hard to work with. But again, for aviation fuel, can be utilized. It has some advantages in that wings that are very cold also minimize drag for the plane. Other options are metal hydrides. So this is metals that can absorb hydrogen, and then when you heat them up, they release the hydrogen. And that might be used in portable applications when you need just small quantities of hydrogen. And then the last one is you can create a chemical fuel. So you can make ammonia or methanol to, again, create bonds that bring the hydrogen together and then release the hydrogen afterwards. So again, the density is low, but it is possible to store the energy. Okay, so now I'm going to usage of hydrogen. So I've talked already how you produce it. I've talked about how you can store it. Sorry. Now I want to talk about how you would use it, right? And again, I'm borrowing this graph from NREL, from one of the Department of Energy Hydrogen Fuel Cell Review Program, where they try to show the whole range of applications, right? So hydrogen is a fuel that produces 0 emissions no matter what. So what you can do with hydrogen is you can actually displace some of the natural gas for heating. So you can use some hydrogen in your furnace. That would mean that at least you would make less CO2. It might actually burn better as well. You can use it, and we use it all the time, to produce fertilizers. So if you can make hydrogen from solar energy, then you can displace all the hydrogen that is now produced from natural gas. You use it for many other chemical applications and for metal refining, for upgrading of oil and gas, and then of course for fuel cell vehicles. So there are many uses for it, in addition to simply electricity production. In fact, I think producing electricity, again, is one of the worst ways of using it in terms of efficiency. You only should do it when you need to. Okay, so in terms of usage, I wanted to focus on the fuel cells because that's what's looked at in my lab, and also because if you want to use hydrogen buses, hydrogen trains, or hydrogen cars, that's what you would need to put in the vehicle. So a fuel cell works almost like in reverse to what an electrolyzer would do. The way the operation goes is you put hydrogen on one side, you put oxygen on the other side. The oxygen can come directly from the air. So you would take air with a compressor from the environment. And then the hydrogen will react following the reaction that you can see there to protons and electrons. It goes to this blue component, which again is a gas-tight membrane, so only allows transport of protons. Protons travel to the other side, mix with oxygen to produce water, and then this water needs to be evacuated. The fuel cell performance is characterized again by the same type of curve as an electrolyzer, but it's in reverse. So now my ideal operation would be a flat line here, but as I produce more current, or if I produce more power, so if you, for example, press on the gas on your fuel cell vehicle, then you have an efficiency loss. And the aim for an engineer to make fuel cells more available is to basically make sure that these losses are minimized and that you can produce as much current as possible. Before that, I wanted to talk a little bit about transportation, because I think a lot of you think of, when you think of fuel cells, you think of cars and buses and so on. So someone asked me the other day, are there any fuel cell cars available? And the answer is yes, but in the countries that have decided that that's one of the options that they want. So Toyota makes their Toyota Mirai, and they do sell it in the US. They have three different versions, and Hyundai has the Hyundai Nexo, which is also sold in the US. All of these cars have about 600-kilometer range as per EPA standards. So for example, the Toyota Mirai driving at 10 kilometers an hour made a record the other day where it reached more than 1,000 kilometers in one charge. And they have a certain consumption that I'll talk in a second. So basically, are there hydrogens on the road? Yes, there are hydrogen vehicles on the road today, and they are used for long distance travel because they allow you to have a longer range that you would achieve otherwise in a conventional vehicle. And I will talk about this in a second, but they also allow you to refuel quickly. So 5 minutes is what takes you to refill your tank completely. In terms of costs, how much would it cost? So that depends on how much the cost of hydrogen is. And since I cannot go to a hydrogen station and tell you, I have to go and find some data on the internet. So this is from the International Energy Agency, and they estimate that the cost of hydrogen produced from natural gas nowadays would be between $0.50 per kilogram to $2 per kilogram. Remember that from green energy is $5 to $10 per kilogram. So I'm making it using natural gas. If that was the case, and taking into account that I only need 5 kilograms of hydrogen, 5.6, to drive 600 kilometers, I would only need half a tank to drive to Calgary. And so half a tank would be 2 kilograms or so. That means that I can go to Calgary for $1.8 to $6.1, which is equivalent to Starbucks latte, which is now a tall one is 2.95. So I think that's reasonable. And then you might wonder, what about refueling? So again, that will depend on the state that you're in. Here, if you want to refuel, you can't. But if you were in California, all you have is you have a fuel cell app that tells you where the gas stations are located and the ones that are online at this moment to go there. And then you simply go there, and it works very similar to what you do these days, which is you have a nozzle. The nozzle gets hooked to the car. When the connection is done properly, a light says, now you can put hydrogen. You press a little button, and then hydrogen goes from the station to your tank. And you can choose two pressures. So if you want to drive short distance or you want to fill half your tank, then you fill it to 350 bar. And if you want the full range, you fill it to 700 bar. So it's actually rather easy. I would say that it's almost easier than filling a blue track for what I've seen on YouTube recently. Okay, so now you know how the vehicles work. Now we can look at what we do again in our lab. So the main problem nowadays with fuel cells is you saw the cost of the Toyota Mirai was $60,000 per vehicle, and a lot of that cost comes to the fuel cell. So how do we lower the cost of the fuel cell? We try to do this by increasing the amount of power that you can produce from the same device. So for example, in 2006, we were sitting somewhere here where a fuel cell stack would cost about $50, between $50 and $60 per kilowatt of power. 2017, 2020, we are already at $20 to $30 per kilowatt hour. But the ultimate target should be down here. This is from a current opinion paper from some researchers at General Motors. So to get these values, what I need to do is I need to remove the water that I produce fast enough. And so that's a lot of the work that we do in our lab. We are looking at new catalysts, and we're also looking at different materials to better understand how water accumulates and what the impact that it has. We do it by experimentation. So for example, here we're running dry with different oxygen concentrations. And you can see when you put more oxygen, the line is a lot flatter than otherwise. And we also do it by simulation, by trying to simulate materials that we image with X-ray tomography. And then we try to also see what the water does in terms of destabilizing operation. We also have a full lab where we characterize these cells and try to understand how the water can be moved from one side of the cell to the other across the membrane. And the last thing that we are trying to do, and I don't think you can buy these devices yet, but I think the ultimate target would be if you want to make hydrogen and you want to use it, make it all in one device, because then you save half the amount of material. So one of the things that we've been trying to do is work in what's called a unitized regenerative fuel cell, which can make hydrogen, but then it can work the other way around. So the problem with doing that is that a lot of the materials that are used in a fuel cell are carbon-based. And when you go to the potentials that you would use in an electrolyzer, they corrode completely. So we had to basically change the materials of the plates to be titanium-based to avoid that corrosion. And then for the catalyst, also the catalysts that speed up water splitting are different from the ones that are used to make oxygen turn into water with protons. So we worked on something called bifunctional layers or bifunctional catalysts. So blending the catalyst or making layers of the different catalysts to try to have one electrode that can work in both directions. And then since the catalysts that are used in the cell are basically use scarce materials, and that contribute a large chunk of the cost of the fuel cell stack, we also started to use inkjet printing technology to make these electrodes, again, to be very, very thin and use very little amount of catalyst. The combination of all this is this evolution in terms of performance for different technologies. So we started somewhere here, and then now we can produce a lot more current than we did in the past. If we run them forwards and backwards, we've been able to show reversible efficiencies of the order of 60 to 50%. If I look at 1 amp, we get efficiencies of 50% or so. So that goes back to the numbers that, again, someone was asking, what is the efficiency? Depends on the device that you make. In a lab scale, at decent amounts of current produced and decent amount of hydrogen production, we're at 50. I could tell you that I'm at 60, but I don't think the amount of current and the amount of hydrogen you produce is good enough. So with all this now, I would say this is a graph that shows some reversible cells that have been done over the past 10 years. Some of the cells that we have at the U of A sit somewhere here, where they have some of the highest reversible efficiencies, and they use the least amount of catalyst. So they are cheap and also have a pretty good efficiency. Okay, so the last thing I wanted to do with you was a quick demo of how this would work. So what I have here in my office is this setup. I have here solar panels on the right. I have a load here on the left. I have an electrolyzer, and then I have a fuel cell located here. And what I want to show is how this whole system would work in situ. But maybe, given the amount of time, I'll just show you a quick video of this. And then if you have questions on the device, I will load it up on the phone. And then I can show you the device real life. But that's more or less the device. Panels can be used when the sun is shining, like our house.
So Mark, we can't really hear the audio of the video.
Oh, sorry.
No.
I will do the audio.
Awesome. So if you can just mute it, because we can hear it really faint in the background. If there is that audio, that little volume thing at the end. But then if you just let us know what's happening.
Yes, hopefully now you can hear it. So what I'm trying to show here is these are lights that will mimic the sun. These are now shining light to the solar panels, which are placed here. And then at this point, I can connect the solar panels to a load, which again would be the equivalent of your house, in order to provide you with the electricity that you would need to run your appliances. Yeah, so there is some light there. The idea that we have with hydrogen is that at the same time that you're powering your house, you can connect this in parallel with an electrolyzer, which is what I'm doing now. When you connect them in parallel, you use the electricity that you can, but any extra energy that is not being used at that specific point in time, you can then use it to produce hydrogen and store this hydrogen in a hydrogen tank. So now I'm connecting the leads to the electrolyzer, and now what you're going to see is the electrolyzer in operation. So you can see now where the channels are, how some bubbles are appearing there. So this is the membrane sits in the middle, and these bubbles are hydrogen gas that is going into this main tube. This main tube brings the hydrogen to this reservoir tank that I have here. The oxygen is on the other side, so it can go into another reservoir. And in this other reservoir, you can either store the oxygen for later use, which is what I did in the regenerative system that I showed you in the last slide, or you can basically sell it, for example, to hospitals, or you can basically dump it into the atmosphere. The hydrogen can then be put into a fuel cell, so that's what you're seeing here. That's a fuel cell stack that breathes air through those little holes. So once the hydrogen has been made, the next thing that we can do is we can turn off the solar panels, which is what comes next. That's the hydrogen that has been produced. That's the stack. And then what I will do is show you next how you can basically power the house once the lights are not on by the fuel cell stack, right? So now I turn off those lights. The light to the house is off. And now I can connect the positive and the negative terminals of the stack to the terminals of the house. And again, replace the sun by the fuel cell stack. And so you would have a complete system where you can basically use your solar panels to some degree day and night transparently by the use of hydrogen as an intermediary between the two. All right, so that's the end of my talk. Just a few last minute remarks to wrap it all up. I hope I've been able to show that our current energy systems is based on fossil fuel, which leads to some problems, including energy security, outdoor pollution, and greenhouse gas emissions. I think, and the data shows that solar and wind technologies are now cost competitive with other technologies, which means that eventually we should start to deploy them seriously. And seriously, we've talked about what seriously means. And as we start to do that, we will run into the problem that we need some daily and seasonal energy storage. And so we need large scale storage, and we have very few options, one of them being hydrogen. Also, that eventually these electrons should also replace things that cannot be replaced with electrons. Again, aviation fuel being one example. So again, hydrogen can play a role into entering other markets that are not electrical. Hydrogen can be produced as a synthetic fuel, which can from a variety of sources, including renewable energy, and can be stored in the quantities that we need for daily and seasonal storage. It can displace fossil fuels. I showed you how we can do it for transportation. For residential and industrial sectors, a lot of the time you just burn the hydrogen, which basically has an efficiency of 100%. Well, 90 something. And then I tried to give you some examples of what we do at the U of A in terms of trying to develop the technologies that we will need to produce hydrogen with the least amount of energy at reasonable prices, and fuel cells, again, for at reasonable prices and that are durable. With this, I will just wrap it up. Just thank you for your attention. Thank the people that fund the lab, Future Energy Systems, for inviting me, and you for your attention. So thank you.
And thank you so much. You can only see me and Cassidy, but we're giving you a huge round of applause. That was such a fascinating talk. I feel like we've learned so much in just an hour and a half. It is 8:29, but do you have a couple of minutes to stick around and answer a couple of questions?
Yeah, no problem.
Okay.
Yes. Yeah, I'm sorry I ran a little bit longer than I wanted.
No worries. We got to see an awesome demo. For anyone who does have to go, we totally understand. You can catch up on this Q&A in the video that we'll post on the Future Energy Systems website. So if you do need to go, we understand. We will not be offended. I'm going to post a couple links in the chat. You can learn more about Future Energy Systems, sign up for our newsletter. Cassidy's going to post a link to the survey so that you can let us know your thoughts. And I am going to post the link to our next event, which is June 22nd. And it is going to be where we launch our new children's book. So if you've got any little ones in your life, we are going to be doing a live reading followed by a Q&A with the creative team around our new book, The Case of the Shiny Roof, which explores all the different ways we use the energy from the sun. Well, not all of them. We've learned more ways tonight, but different ways we use the energy from the sun. So that is our next event in June. And then Energy Talks will be back in the fall. So we will be off during the summer, but don't worry, we will absolutely be back. So for anyone who does have to leave, thank you for coming. Now we're going to dive into the questions because we got so many of them sent in as we had that last section. So this question was actually sent in advance. Someone who couldn't come tonight, but desperately wanted to know the answer to this question. They sent it in advance. So given that electrolyte flow pathways have a significant effect on alkaline electrolysis efficiency and your expertise in modeling fuel dynamics in fuel cells, has your group considered doing research and engineering towards optimization of electrolyzer flow fields? I don't know the words I just said, but I hope that you can address that.
Yeah, so it's a good question. So So yes, we are trying to simulate the flow field as well, but we have focused on PEM, not as much in alkaline. So it's something something that at this point we have explored less than the actual electrode, simply because in my opinion, it is the electrode that is the one that could have the biggest impact, because it's the most expensive component to some degree. But happy to explore more on the flow fields. Yeah. We didn't touch on that. Simply, it's a matter of time. And I always, we've always focused on the part that contains the expensive catalyst, which is the one I think has to be minimized first.
Absolutely. Well, thank you for addressing that. The next question is minus 259 Celsius, the boiling point or freezing point of hydrogen?
It's the liquefaction point. So going from gas to liquid.
Okay. There's so many that came in, so I'm just going to go through them rapid fire. Would replacing natural gas methane with hydrogen for heating homes require the replacement of gas lines to our homes?
That's a good question. So blending can be done up to 5–10% with natural gas with the same pipelines. After that, more research needs to be done, but potentially yes, because hydrogen is a smaller molecule, and so it can leak in materials that methane might not leak. So there is some work that needs to be done in liners. Also, there is also something called hydrogen embrittlement. So for some materials, a small crack will be expanded by hydrogen because it can go in there and increase the crack size. But up to 10, I think it's been proven to be okay, and people are researching blending to higher percentages to see if that's okay with the current grid infrastructure.
Always one of those things where there's just more questions, more research to be done, so many more. Next question is related to those fuel cell vehicles. How do cold temperatures impact range of fuel cell vehicles due to the impact on the pressurized gas?
Oh, that's a good question. Well, the biggest impact is you have to start it and you're producing water. So cold start is a big issue in fuel cells. So for example, Toyota goes to Yellowknife to test their vehicles at very cold conditions. So they go there and they start at a minus 30 degrees. And so there is a whole bunch of engineering behind removing the water before it freezes. So that's the biggest challenge. In terms of efficiency, again, the fuel cells are about 50% efficient. So you have extra heat that you can use to heat up the cabin. So the efficiency is not as impacted as you would, for example, on a battery vehicle where you don't have any heat being produced because they are very efficient. And then in terms of the gas compression, I don't know how much I can say, only that there are engineering solutions to recover some of the compression energy and to make sure that that again, when you expand the gas and it does cool, that doesn't lead to any problems.
Okay, great questions coming from the audience. Thank you all. Where do you see kind of the fuel cell vehicles, electric vehicles, hydrocarbon vehicles? Where do you see kind of that combination of vehicles in the future? Do you think hydrogen cars are a viable competitor for electric vehicles in kind of what kind of time scale?
I think that there is going to be a range of vehicles. So I think there is advantage to every one of them. So an electric vehicle is more efficient. And so for short range city commutes, I think electric vehicles are more competitive than fuel cells. I think fuel cell vehicles have an advantage for fleet deployment. So when you need to drive a cab, you cannot park and charge it for 2 hours. You want to be on the go all the time. For buses, again, they have a benefit. And for any vehicle that is heavy, you have an advantage. So for example, in the US, funding for fuel cell vehicles is now focused on heavy duty vehicles. So trucks and buses. And funding for EVs is focused on normal small cars. Ideally, we will find a sweet spot in the middle. So batteries will get better and they will offer longer range, and fuel cells will get better and they will be able to be more cost effective in the smaller vehicles. And eventually we will find the sweet spot where we can harness the benefits of both, I think.
Really coming back to that point of climate change has no single solution. There's going to be a bunch of little solutions. So EV and hydrogen cars don't have to exist all by themselves. They can exist together.
Correct. Yeah.
Absolutely. And you may have mentioned this when you were talking about brown and blue hydrogen, but we had a question surrounding the idea of, are blue and brown hydrogen worth pursuing, or does it just extend our reliance on fossil fuels?
It's not a matter of if it's worth or not. It's that we need to replace 85% of the energy produced. I think if you can, it's not that, you have to rely on them. Like I just show you some examples of how much it will require to simply keep up. And you now need to displace all that. I think it's all hands on deck. Whatever helps. I don't think it's the ultimate path, but if you need to deploy the amount of wind turbines and the amount of solar panels that are required to keep up, plus to start displacing in the meantime, you can certainly use blue hydrogen. Brown hydrogen, it doesn't excite me that much. Like you're trading one problem for another. But I think blue hydrogen does have more opportunity.
Okay. Last question. I mean, there are lots more, but I don't want to keep everyone. So last question. If you could tell everyone in Edmonton, hydrogen is so much in the news right now. We've seen a few different hydrogen conferences within the city. But if you had everyone listening, what is one thing you want people to know about hydrogen when it comes to energy, climate change? What is the message you want to get out?
I would say read about it so that you understand what it is, the different pathways to make it, how it is produced, and to understand that having a conference in hydrogen does not make us an expert on hydrogen. It seems like we wake up to hydrogen about 3 months ago, and now everyone thinks about hydrogen, but I doubt 90% of the people that talk about it understand the full chain. And I think it will be a waste to make uninformed decisions, because eventually they come back to hunt the people that actually work on those. And so, yeah, read, don't come up to don't let someone convince you that hydrogen is amazing. Hydrogen is one more solution. It has good and it has bad. And you need to do it properly for it to have benefits, like everything else. If you eat too much sugar, is great in moderation after running a marathon, but probably if you eat 2 kilos of sugar, it probably will not be very good for you. So this is a little bit the same.
Absolutely. And you're all on your first step to learning more about hydrogen by joining here tonight. And hopefully Mark's introduced a lot more questions for you to go out and hopefully find the answers to. So thank you, Mark. Again, huge round of applause. That was a wonderful talk. We're so excited that you're able to join us, and we've all learned so much tonight. Thank you all for joining us. We really appreciate you spending the evening with us. If you're heading to watch the hockey game, good luck. We'll keep our fingers crossed for you all. Cassidy, any last remarks from the library?
No, I think you've covered it. I'll just echo your thank you to Mark and to everyone for joining us this evening.
Wonderful. Well, thank you, everyone. And we hope to see you at our event in June. If you are not coming to that, we hope to see you again in the fall. So thank you all.
Thank you.